Hello, and welcome to Lecture 6. This week, we're going to discuss new concepts of work, energy, and power. To do this, we're going to apply what we've already learned about kinematics, the motion of objects, and dynamics, the application of forces, to understand these new concepts. Work, energy, and power will be concepts that we use to understand how objects behave when they interact. One of the types of problems we are going to solve is we are going to introduce a new concept of conservation to these quantities that we begin to talk about. The first new concept we are going to consider this week is work. It's very important that you think of work as one of the words that has a specific meaning in physics that may be different from the way you interpret it in everyday life. Work is the product of the force applied and the displacement of the object. When we look at the formula, the cos of theta means that only the component of force that is in the direction of displacement contributes to the work. If our force is applied at some angle theta, and the object moves along a displacement that is on the horizontal axis, then the cos of theta multiplied by the magnitude of the force yields the component of the force that is only in the x direction. Some of the consequences of this statement. If displacement is horizontal and the force applied is vertical, in this case theta equals 90 degrees and cos of theta equals 0. So despite applying the force in the vertical direction, you completed no work. Also with horizontal displacement and a horizontal applied force, in this case theta would be equal to 0 degrees and cos of theta is equal to 1, so we would have all of our force contributing to the work. Looking at our formula, you should see that the W representing work has no vector over top, and this should assure you that work is a scalar quantity. Looking at an example that asks us how much work does the woman do on the crate, we can see that there's an applied force of 120 newtons and a displacement of 3 meters. The applied force, represented with the purple vector, is parallel to the displacement. So with a parallel application, we take theta equal to 0, and we can switch to calculating that our work is equal to the magnitude of the force applied multiplied by the cos of theta multiplied by delta x, and we could substitute our known values, and we would get a work equal to 360 Newton meters. This is the amount of work the woman does on the crate. Some of the assumptions that we had to make here is that there was no consideration of friction. We also didn't need to know the mass, so the mass of the crate doesn't matter for work. And without mass, we have no way of knowing how this crate moves while the force is being applied. In fact, if all we are considering is the amount of work the woman does on the crate, then none of those considerations make a difference. Those considerations will come up for a different type of problem later in the lecture. We should consider work as a transfer of energy. In that sense, we need to think of energy as its own concept. Energy is described in your textbook as a form of currency. More specifically, energy is a way that accounts for how much motion we can have. It's important to understand that energy cannot be created or destroyed, it must be transferred. Energy is measured in a unit called the joule, and in fact the joule is defined as a Newton multiplied by a meter. We should note that work is also measured in joules. We saw that work can be calculated based on the amount of force applied over a displacement. Work can also be calculated as the change in energy of a system. So here, delta E represents change in energy. Now, there are multiple forms of energy. We can think of energy in terms of sound and light, nuclear energy, thermal energy, even electromagnetic. For our unit, we're going to focus on mechanical energy. Mechanical energy is made up of two types of energy. It's made up of kinetic energy and what we will refer to as potential energy. These two types of energies, combined as mechanical energy, will help inform us about the behavior of moving objects. Let's look more closely at those two types of energies. Kinetic energy is the energy of motion. It is proportional to the mass and velocity squared. So the kinetic energy of any given object is the mass times the magnitude of velocity squared, all divided by 2. Whenever we do work on a system, we are often transferring energy to or from the object in the form of kinetic energy. With more knowledge of our previous system, we could think if the woman is applying a force and it contributes a net force, then the object will have an acceleration. Thinking back to our kinematics equations, if the object has acceleration and it's applied over a longer and longer distance, then we have a greater and greater final velocity. And as you can see from the kinetic energy equation, more velocity will mean more kinetic energy. It's important to understand that kinetic energy helps us think about the amount of possible motion. So that means we are using the magnitude of velocity, and that kinetic energy is a scalar. So it has magnitude but no direction. Let's consider an example. An arrow shot into a target embeds itself 4.2 centimeters into the target. Given the initial conditions below, how much work did the target do on the arrow? So we're given a displacement and an initial velocity and a mass. And if it's embedded in the target, we can assume a final velocity, which may lead you to think of approaching this question with the first work equation. But remember, work is also defined as the change in energy, which means if we know the final kinetic energy and the initial kinetic energy, we can calculate the amount of work. So if we know the initial velocity is 5 meters per second and the mass is 0.015 kilograms, using kinetic energy is equal to 1/2 of mass multiplied by velocity squared, and substituting our information, we can get an initial kinetic energy of 0.1875. Our units here can be a little confusing. So we have units of kilograms and meters per second that get squared, which leaves us with weird units of kilograms meters squared per second squared. Recall that a kilogram times a meter per second squared is a newton, which leaves us with newtons and meters, which is our units of joules. So we have the correct units for our energy. If we repeat the calculations for our final setup, we have a velocity initial equal to 0 meters per second, and a mass equal to 0.015 kilograms still, and kinetic energy using the same equation. So our final kinetic energy is 0 joules. If we go back to our work equation, that means we will see that we have 0 joules minus 0.1875 joules, which gets us negative 0.1875 joules. While work is a scalar quantity, we can still have negative symbols that have meaning. This does not refer to direction, but it does tell us something about how the energy is transferred. What does negative work mean? It means the entity doing work on the object is removing energy from the system. So as the arrow impacts the target, it slowly loses its kinetic energy as it's transferred out of the arrow and into another system or other forms of energy. Let's look at potential energy now. Potential energy is due to gravity, so its real name is gravitational potential energy. We call it potential energy for shortness and convenience. This is the energy stored in an object with reference to a given vertical position. For many of our calculations, this gravitational potential energy is going to be specific to Earth. One of the main ways we calculate potential energy is looking at the change in potential energy. Often what's happening here is we do work to lift the object to a new position. So if we want to calculate change in potential energy, we need to know the mass of the object. We need to know the acceleration due to gravity. And note that this is the magnitude of the acceleration due to gravity. We do not have the vector arrow, so we do not use that negative value here. And we also have the change in height of the object. If we have the convenience of setting our reference point as 0 meters and having that line up with the initial or final position, then our formula simply calculates the original amount of potential energy stored, and we wouldn't be calculating a change in here. So with reference to the point of 0, we could calculate an instantaneous potential energy. You can see here that this equation is linearly proportional. So more mass or more height means more potential energy. I like to think of potential energy for the potential of things to go wrong. Picture a physics textbook, one of the old school ones. If that physics textbook is just sitting on the ground with a height of 0, there's no potential for anything to happen. But when you lift that physics textbook to the top of a tall shelf and it's perched precariously on the edge, you suddenly have potential for a lot of things to go wrong. Let's take a moment to look at a potential energy example. What would be the minimum amount of work done to lift a 3.6 kilogram physics textbook to a 0.73 meter tall desk? So we have a desk, and that desk is 0.73 meters tall. And if we have our physics textbook with a mass of 3.6 kilograms, we can take the ground as position 0 and our final position equal to 0.73 meters. Remember, again, if we're being asked for work here, we want to think of work as the change in energy. So in our case, if we're looking at the initial position and the final position where the textbook is resting, we would have a change in potential energy, which means we would have the mass times gravity times position final subtracting position initial. And we see that we have added 36.01 joules of potential energy. You might be asking yourself, why does it say the minimum amount of work done? Well, in this case, we've again not mentioned friction, and we've not really talked about exactly how the textbook moves from bottom to top. So in this case, by saying minimum, we know that at the very least we have to contribute 36 joules worth of energy. And if anything else happens, like wind resistance or an inefficient lifting path, then it would take more energy to do this job. One of the assumptions made that's not well visualized here is that we've applied just enough force to keep a constant velocity. If you decided you wanted to apply much more force to attempt to do the job more quickly, then you'd be applying force to accelerate the book up, but as you came closer to the top of the desk, you would have to apply force in the other direction to slow the book back down. So you'd be doing work to put extra energy into the kinetic side of the book on the way up, but you would also have to do more work to take that energy out before bringing it to a rest. So by assuming just enough force to keep the book moving, you get an average amount of work done that it would take to just change the height. With that in mind, we might want to mention one more characteristic. If we want to think about doing work faster, then we have a measurement for that, and this is called power. If we complete work with different levels of intensity, so we do it faster or slower, the rate at which energy is transferred is referred to as the power. So not on screen is the formula that power is equal to change in energy over change in time, which is the same as work over time. So note that this would be a joule per second, and this unit is referred to as the watt. Many of you have seen this unit before. When you purchase light bulbs, they are measured in units of watts. That gives you the power of the light. While we're not going to look at an example right now, note that many of our calculations for this type of problem will focus on calculating the average power applied. We're going to leave this topic for now and most likely look at it in more detail when we come to our electricity unit. There are some restrictions on conservation of energy. In addition to the absence of external forces, you'll see that the type of problem we solved tended to be single body problems. Conservation of energy will apply to two objects during a collision, but not in every type. We have generally two types of collisions that we consider. We can consider collisions that are perfectly elastic or perfectly inelastic. And it can be difficult to keep these straight. So I like to think of them as elastic collisions are efficient collisions. And I say efficient because they're efficient at transferring all of the mechanical energy from one object to the other. So in elastic collisions, mechanical energy is conserved, and these are often types of collisions where objects completely bounce off each other. The other type of collision are the inelastic collisions. And keeping with our previous thought, I think of inelastic collisions as inefficient collisions. And these are the type where mechanical energy is lost. So mechanical energy initial does not equal mechanical energy final. Now remember, energy cannot be created or destroyed. So in these types of collisions, the energy's been transferred to other forms. So the surface of the object may be permanently deformed. The two objects might collide, creating some noise, which is energy. The objects could have friction between each other and slip a little bit and bleed energy off into thermal energy. All sorts of inefficiencies show up. Inelastic collision is that the objects will not completely bounce off each other. In fact, the objects often couple together. Now you'll see that I added perfectly in pink to both of these words. That's because the truth is that all collisions in the real world fall somewhere on a spectrum, which means moments of the collision are sometimes elastic and sometimes inelastic, and it all depends on a lot of complex factors. For our course, you'll be told whether or not a collision is elastic or inelastic, and then you will work from there. So in an elastic collision, you can use the conservation of energy to solve for missing values, but in inelastic problems, you cannot use the conservation of energy to solve for missing values. Luckily though, in both of these cases, there's another characteristic of motion that is conserved. No matter where on this spectrum that a collision occurs, all collisions will conserve something called momentum. Let's look at what momentum means. So momentum is similar to kinetic energy in that it's dependent on the mass and velocity, but it's calculated slightly differently. In this case, it's the product of mass and velocity. There's no squaring. The other key difference is that momentum is a vector quantity, which means that direction is very important when we think of momentum. If you consider two objects and you give both of those objects the same mass and you give both of those objects a speed of 2 meters per second, but in consideration of velocity, one object is moving to the right and the other object is moving to the left, then their momentums are not equal, even though their kinetic energies are. One of the other things that's very important here is that when solving problems, an object with a zero momentum still has momentum. And we have to be careful not to exclude it from our considerations when looking at the before and after scenarios. So we said in all types of collisions, momentum is conserved. So this means that the sum of all momentum values in the final situation has to be equal to the sum of all momentum values in the initial situation. And again, these are vector quantities, so direction is important. We're going to look at an example in just one dimension, but you should note that if we ever had 2 and 3 dimension problems, because these are vectors, we would have to break them down into their components. So let's consider two objects again. We have object 1 with a mass of 0.30 kilograms and an initial velocity of 2.5 meters per second. And let's have object 2 with a mass of 0.40 kilograms and an initial velocity of negative 3.5 meters per second. And let's have these objects undergo a perfectly inelastic collision. So that means object 1 and 2 have stuck to each other. They have not bounced off each other in the slightest. And our job will be to find the final velocity of the two of them stuck together. So this is a situation where we apply conservation of momentum. So we need to consider all of the momentum after the collision and all of the momentum before the collision. So after the collision, we have one new object with a combined mass of mass 1 and mass 2 and a final velocity. And before the collision, we had mass 1 and velocity 1 and mass 2 and velocity 2. So we know that we're solving for our final velocity, so we can rearrange by dividing out that total mass. And we can substitute our values. We can plug all of this into our calculator, and we should get negative 0.92857, a bunch more information, meters per second. What's this value telling us? Well, it means that if our initial velocity was in the negative direction for object 2, that object 2 had enough momentum to collect object 1 and keep moving in that direction. The kinetic energy after the collision is about 1/10 of the kinetic energy before the collision. I want you to take a moment and confirm this for yourself to see that conservation of energy could not apply to this type of collision. What about a perfectly elastic collision? Elastic collisions are usually set up with one stationary object. So if we had objects of 0.30 kilograms at rest and an object of 0.40 kilograms with a velocity of negative 6 meters per second. In this situation where we have one stationary object and one moving object, the textbook gives us some equations. While the textbook goes through the derivation, I would not ask you to have to do this on a test. Even more, I'm going to help you simplify these two equations. If you want to find the final velocity of the object that was initially moving, then you use the first equation, which is the mass of the moving object, subtract the mass of the stationary object, divided by the sum of the mass of the moving object and the mass of the stationary object. And you multiply that by the initial velocity of the moving object. The other equation is that if you want to find the final velocity of the stationary object, then you take 2 times the mass of the moving object divided by the mass of the moving object added to the mass of the stationary object, and again multiplied by the velocity of the moving object in the initial frame. Then we can solve for the velocity of the two objects. So in this case, the moving object is the pink one. So if we want to solve for the pink object's velocity, that means we would substitute the values 0.40 kilograms, subtract 0.30 kilograms, dividing by the sum of those two values, and multiplying by that initial velocity. And we get a final velocity equal to negative 0.8571, and a lot more information, meters per second. What about the object that was stationary? Well, substituting our values, 2 times 0.40 kilograms divided by the masses of the two added together, multiplied by that initial velocity of the moving object, we get negative 6.8571 meters per second. And we could double check to see if the kinetic energy here was conserved. So in our initial phase, we had a kinetic energy that was entirely in the one moving ball. So we had a kinetic energy of 7.2 joules. And then after the collision, we have two kinetic energies. So we have 1/2 of the 0.30 kilograms traveling at negative 6.85 meters per second squared. And we have 1/2 of the 0.40 kilograms traveling at negative 0.85 meters per second squared. So after the collision, we have a kinetic energy in our ball that was originally stationary of 7.05 joules, and in our ball that was originally moving of approximately 0.14 and a bit more information, joules. So you can see that kinetic energy was conserved at 7.2 joules. With this new information about collisions, let's go back to a topic from a previous lecture. Earlier in the semester, we looked at types of collisions considering their general effects on velocity. Now we know that the collisions are actually governed by momentum. So while we admitted it was a general look previously, we now know that we need consideration of the mass of both vehicles in addition to their velocity. We still don't have enough ability to fully consider collisions, as they are very messy, inelastic conditions. But we can still look at the general consequences of each direction of collision. So in our examples, we're going to consider a head-on collision between a 1,000 kilogram vehicle moving 5 meters per second and a 2,000 kilogram vehicle moving 2.5 meters per second. And we can look at a T-bone collision between the same vehicles. And finally, let's look at a sideswipe collision between the same two vehicles as they travel towards each other with relative angles of 30 degrees each. First, let's look at the head-on collision. If we treat up as the positive direction, we can see that this is a one-dimensional problem. The momentum of the black vehicle is equal to 5,000 kilogram meters per second, and that's in the negative direction. And the momentum of the blue vehicle is also equal to 5,000 kilogram meters per second. These two values are equal in magnitude, but opposite in direction. Remember, we cannot say that two momentums in opposite directions are equal, so they will cancel out, which means that our state after the collision should also have a momentum of 0. So one possible outcome is that both vehicles come to a complete stop. Again, just like we saw with our consideration of velocity only, these types of collisions would have the greatest total impact on each vehicle. What about our T-bone collision? Well, in this case, the magnitude of our momentums are again the same value, but now we have 2 dimensions worth of directions. So we can take to the right of the screen to be our X direction and to the top of the screen to be our Y direction. We have to look at our total momentum in each component. So our X direction would have 5,000 kilogram meters per second meters, and our Y direction would also have 5,000 kilogram meters per second. So if these two vehicles inelastically collided, they would have some amount of being stuck together, and their new resultant momentum would have a component of 5,000 in the y direction and a component of 5,000 in the x direction. So we would likely see the two vehicles having a combined momentum of 7,071 kilogram meters per second, which would correspond to the two vehicles having a velocity final of approximately 2.4 meters per second at an angle of 45 degrees. So we can see that both vehicles will experience a much less drastic change in velocity. And finally, let's consider the sideswipe collision. In this case, our x direction is contributed to by both vehicles. So we have 1,000 kilograms multiplied by 5 meters per second times the cosine of 60 degrees, and that's contributed by the black vehicle. And the blue vehicle contributes 2,000 kilograms multiplied by 2.5 meters per second and the cosine of 120 degrees. You should see that this is just the original 5,000 kilogram meters per second magnitude for each of them, scaled by the two cosines. These two cosines are actually equal and opposite, so our x direction has 0 momentum. We can complete a similar calculation for the y direction, this time using the sine. Which gives us a momentum in the y direction of 8,660, which would give the two cars a approximate velocity final of 2.89 meters per second. So you can see this would have the smallest impact of all the collisions on the lighter vehicle, and the heavier vehicle wouldn't see an abrupt stop at all. It actually would pick up a little bit of speed. Now, all of these collisions are approximate. They involve some fairly complex calculations to consider the crumple and crash zones of the cars, to consider the damage in the middle of the collision that would change the way the cars bounce off of each other. There's also considerations of friction everywhere. And it really depends on the distribution of the mass on the two cars. All of our force applied calculations so far have relied on a concept that we haven't actually mentioned. When we apply forces to objects, we have to consider them as applying through the center of mass. When forces are not applied to the center of mass, then the objects tend to move in unstable ways. They'll spin and rotate. So we need to look at what that center of mass is. So let's take the example of a car. If we take the back end of that car to be x is equal to 0 as position, and the front end of the car as x to be equal to 3.3 meters, the center of mass is trying to figure out what the average distribution is of all the mass in the car. So we'll simplify this a little bit and we'll consider some of the major components, like a car likely has 40 kilograms of fuel in its tank, and we can say that's at a position of 0.5 meters from the back. And cars likely have engines, which contribute a significant amount of mass, say 350 kilograms, and we'll put that as 3.0 meters from the back. And we can even consider the driver of the car, as that's another 80 kilogram mass, and we can say it sits back from the front, but it's 2.5 meters from the back of the vehicle. So how do we calculate the center of mass? Well, the center of mass is a position, and we calculate that position by taking the sum of all the masses multiplied by the position that they happen at. And then we're going to divide that by the sum of the total mass. If you're familiar with statistics calculations, and for lack of a better term, because we don't want to confuse weight and mass, this formula is a weighted mean. It gives certain masses more value based on their position. So let's substitute all of our values for this equation. The sum of every mass times its position means that we would go to the 40 kilogram fuel tank and multiply it by its half meter. Then we'd add to that the 80 kilogram passenger multiplied by its 2.5 meter position. and then add to that the 350 kilogram engine multiplied by its 3 meter position. So when we work on that, it looks like the following. So when we complete this calculation, we find a center of mass equal to 2.70 and a little bit more information. So if we look at our diagram, which wasn't to scale at all, this would put the center of mass in the x direction approximately there. So what does this tell us? Well, if we were to be in that T-bone collision, and the collision actually impacted right on the center of mass, then that would push the whole car evenly in the direction of the collision. But if that collision were to catch the back end of the car, so it hits outside of the center of the mass, then what happens is the center of the mass comes a focal point for the whole car to rotate around. This is why collisions awfully seem very chaotic and spinny. If we don't hit directly on the center of the mass, everything moves relative to that point. Now, I'm not going to ask you to do center of mass calculations on this week's quiz, but you may need it for a couple of questions in the assignment, and it will be important for us when we move on to next week's lecture. I want to leave you with a think about this. Last lecture, the think about this was a hard problem. This lecture, the think about this is a good prep for your quiz. If a 2 kilogram projectile is launched from ground level with an initial velocity of 10 meters per second at 90 degrees, calculate the mechanical, potential, and kinetic energies for the projectile when it is at each of the 4 points below. So at its initial height, so the instant that it is launched, find all 3 energies. Then at a point in time when it's traveling 5 meters per second, complete those calculations. Again at its max height, and finally when it's 1 meter above the ground. I'm willing to give you a hint here that this question is very similar to the swing set question. Let's begin to wrap up our lecture. This lecture we introduced a lot of new equations and formula. I'm going to release your formula sheet shortly, and you can have this for the quiz and you can have this for both of our quizzes this week. Our first formula here was our basic definition of work. Our next formula is the work energy theorem, saying that work is equal to the change in energy. We briefly talked about calculating power as the rate of change in energy, but the important equations for this unit are these ones that tell us how to calculate the kinetic energy and the potential energy, the law of conservation of energy, then moving on to calculate momentum and the law of conservation of momentum. Finally, we introduced an equation to calculate the center of mass. With all of those equations this week, we examined how applied forces will affect our motion. We introduced the concepts of energy and conservation of energy to better understand the motion of objects and how they transition to different phases. We introduced momentum, and we used momentum and the conservation law to think about the motion of collisions. If you've had trouble with the think about this problem, I'll give you one more hint. The mechanical energy is constant, which means for all 4 points, it is equal to 100 joules. Good luck, and we'll see you in class.